Today we are taking a look at the very important concept of continuity. Alright, so continuity is like limits. Continuity is in the background of much of what we do in calculus. In order for a function to have a derivative, the function must be continuous at that x value. So, continuity is very important in calculus. Alright, let's take a look at visually what continuity means. Now, we have already, way back in Unit 1 of this course, we started talking about continuity. So this shouldn't be anything earth-shattering for you. I think that continuity is very easy to see visually. So let's take a look at it. So a function is continuous. In short, if I can draw the entire function without lifting up my pen or pencil. If you can draw the entire function without lifting up your pencil, which means no asymptotes, no holes, no jumps, things like that. So if you can do that, this function, I'm going to call this f of x, I'm going to say f of x is continuous for all values of x. This for all values expression we use quite a bit. So we have a symbol for that, for all values, or for all, just for all, period. And that is that capital V with a bar through it. That means for all, for every, for each, all of those, that variety. Okay, so this function is continuous for all values of x. Now, one type of discontinuity would look like this. What if there was a hole in the graph? What if there was a hole in the graph right there? And so to draw this graph, I would have to pick up my pencil or my pen right there because I could not draw through that hole. If I call this, let's call this g of x. G of x has a point discontinuity. That's what that's called, a point discontinuity. At that x value. Let's give that x value some number here. Let's call it x is equal to a. Alright, so we'll say G has a point discontinuity at x is equal to a. So a hole is a point discontinuity. And this is the only type of what we call a removable discontinuity. That's a removable discontinuity. A hole is the only type of removable discontinuity. All right, another type of discontinuity would be if you have a vertical asymptote. If you have a vertical asymptote somewhere. Let's say that we have some function and it's going along fine, and then it has an asymptote coming this way, and maybe it has an asymptote going this way. Let's make this one more simple. We'll just have it go like that. Alright, so this function, which I will call h of x, h has what is called an infinite discontinuity. An infinite discontinuity. Alrighty, so it does not matter that both sides are going to infinity. It is still an infinite discontinuity. At x is equal to, and we'll call this a again, that x value a. Alrighty. Okay, so an infinite discontinuity means you have a vertical asymptote. And this is not a removable discontinuity. We call it a non-removable discontinuity. All right, the other type of discontinuity would only exist if you had a piecewise function. I shouldn't say that. I can think of a couple of functions that's not true. Most often, though, it's a piecewise function, and that is a jump discontinuity. A jump discontinuity. Let's say this function is going along just fine, and then it stops and then picks up somewhere else. And once again, we're going to call this x is equal to a here. All right. So this is a jump discontinuity. We'll call this function j. J for jump. How about that? So j has a jump discontinuity at x is equal to a. All right. So a jump discontinuity means that the limit from the left is not equal to the limit from the right. Okay, that's a jump discontinuity. In fact, let's write that down. The limit from the left is not equal to the limit from the right. Alrighty, and these are both types of non-removable discontinuities. Alrighty, in class we're going to discuss with your table mates what a definition for continuity would be. So what would be a rigorous definition for f continuous at x is equal to a rigorous one. So like a mathy one that could be in a textbook. That's what we're looking at, okay? So I would have you guys discuss this and stuff, but since I'm not with you there, we're going to just, in fact, if you guys want to pause and discuss it, that's fine. But I'm going to go ahead and give it to you. So f of x is continuous at x equals a. Continuous at x is equal to a. If and only if the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. That has to be true. And they both have to equal f at a. So here the limit from the left is equal to the limit from the right, but it's not continuous because they are not equal to f of a. Okay? Alright, so this is our definition of continuity. Alrighty? Okay, if a function is not continuous at a point x is equal to a, we say that the function has a discontinuity at x equals a. There are two kinds of discontinuities, removable and non-removable. So let's talk about removable. And again, I might in class have you guys discuss what a rigorous definition of a removable discontinuity is. When you see the word removable discontinuity, I want you to think whole. So what would be a rigorous definition for a whole? Non-removable is either a vertical asymptote or a jump. Okay, so if you want to pause, discuss this, great. Otherwise, let's go ahead and jump in. So f of x has a removable discontinuity at x is equal to a if, and I could say if and only if, Okay, the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. They have to be going to the same spot from the left and the right. However, this is not equal to f of a. That is removable discontinuity. Okay. All right. So, non-removable. How could we describe a jump or a vertical asymptote? F of x has a non-removable discontinuity at x equals a if the limit as x approaches a from the left is not even equal to the limit as x approaches a from the right. And remember, infinity does not count, right? Infinity is not a number. So if you don't exist, you can never equal another thing. It doesn't matter. Okay, so again, think whole for removable. For non-removable, think vertical asymptote or jump. Alrighty? Okay, let's take a look at some ways that you might be asked about continuity. So some examples. State the values, if any, of x at which the function has a discontinuity. So if your function is rational, the only thing that would make it discontinuous, not continuous, would be the denominator. Because we cannot have 0 in the denominator. So the only x value, I'll say g, is not continuous at x is equal to -2. G has a discontinuity at x equals -2, and only there. Everything else is continuous. All right, let's take a look at a piecewise function. For piecewise functions, which we see quite often when we're asked about discontinuities, okay, what I do is first of all I take them piece by piece. So alone, this is a parabola, and all parabolas are continuous. Alone, this is a line, and all lines are continuous. The only place that we might have a discontinuity in this case is at the changing point. I have a parabola, I have a line. The question is, at 1, do they meet up? Does the limit from the left equal the limit from the right? So to find out, it's really simple. All we have to do is put 1 into this x and put 1 into that x and see if we get the same number. So 1 squared plus 3 is equal to 4. 5 times 1 minus 7 is equal to -2. They do not match. So since they do not match, we have a jump discontinuity. Okay, so I will say f has a discontinuity at x is equal to 1, and only 1. Okay, and for the sake of your notes, the limit as x approaches 1 from the left, that's -2. The limit as x approaches 1 from the right is 4. If I were proving it, I would need to say this. Okay, if I were proving it. All right, number 2. State the value or values of x at which f has a discontinuity given this one. So again, alone, is this the same thing? No. That looks like exactly the same thing that I had before. Is it not the same thing? Oh, it says, I have a little note to change this. We're going to change this to get rid of that 7 and make it a 1. I hope I remember to do that in your, well, I know I didn't remember to do it in your notes this time. Next year. Next year. Okay, change that 7 to a 1. All right. So, again, if I put 1, now when I put 1 in for x, I get 4 for that piece. If I put 1 in for x here, I get 4 for that piece. So this parabola meets this line when x is 1. Okay, their limits are the same. Okay, and if we put, so I know that the limit as x approaches 1 from the left is equal to 4, and the limit as x approaches 1 from the right is equal to 4. What is f at 1? F at 1 is still 4. If all three of these things are the same, then we can say that f is continuous for all, you can use the symbol if you want, for all x. If you don't like that symbol, just write out for all. Not a big deal. Okay. All right, number 3. Find the value of the constant k that makes this function continuous. Well, I have a parabola here. I have a line here. Individually, they are continuous. The only place that they might not be continuous is at 1. I'm going to put 1 in for x, and I want to set it equal to what I get when I put 1 in for this x. I have 4 is equal to k minus 7, so k is equal to 11. That is the value of k that makes g continuous. Number 4, which of the following is continuous at x is equal to 1? All right. Well, let's see. For this piecewise function is equal to this, but only if x is not equal to 1, which would make that denominator 0. I can factor that numerator, and it factors into x minus 1 times x minus 1. Because x cannot be 1, I can cancel these, only because x cannot be 1. And that leaves me x minus 1. Okay? Now if I put 1 into the remaining x, I get 0. So this thing goes to 0 at x is equal to 1. The bottom piece is 1, right? And there's no x in there, so that is 1. These two pieces do not match when x is 1, so f is not continuous. Okay. Is this function continuous at x is equal to 1? Okay, well, it's not continuous at x equals negative 1, but that is the only discontinuity g has. So yes, g is continuous at x equals 1. All right, but this one? Well, individually, this is a line, this is a line. Put 1 in for x, and I get 2. Half of 2 is 1, plus 1 is 2. If I put 1 in for, well, there's no x to put 1 in, so it's just 2. 2 is 2, right? They are the same. And it's defined when x is 1. So yes, h is continuous at x is equal to 1. So 2 and 3 are the right answers here. C. Alrighty. How else could they ask? Let f be this piecewise function. What value of k makes f continuous? Well, if I put individually, this is a cubic function, and every polynomial function is continuous by itself. This is a parabola. Every parabola continuous by itself. The only spot that we might not have a continuity is when x is 1/2, the changing spot. So I'm going to put 1/2 in for all the x's and set these two pieces equal to each other. If I put 1/2 in for x cubed here, I'm going to have k over 8. If I put 1/2 in for this x, I'm going to have k over 2. And I'm setting that equal to, put 1/2 in for this, I'm going to have 32 over 4 minus 2. Okay? How would I do this? I would probably right now multiply both sides by 8 to get rid of those fractions. You might do it a different way, and that's fine, but this is the way I choose to do that this time. So this is going to be a k, this is going to be a 4k, this is going to be a 2. This is going to be a 64 minus 16. That was really a silly way to do this. I should have done 8 minus 2 is 6, and 6 times 8 is 48. I'm going to do it that way. Okay. Now I have negative 3k is equal to 50. Yeah? So k is equal to negative 50 over 3. Which is not one of our choices, and I have a little note here. Okay, I clearly did not update my notes before I copied it out for you guys. My notes say for this one to change to negative 50 over 3. So we'll call that answer B, and hopefully I will remember to change that for next year. We will see. Didn't happen this year. Alrighty. Number 6. No changes on number 6. Alrighty. The graph of G is a piecewise. The graph of G, a piecewise function, is shown on the right. Which of the following statements is true? G has an infinite discontinuity at x equals 1. Is that true? An infinite discontinuity can only be a vertical asymptote. So is there a vertical asymptote at x equals 1? Yes, there is. So that is true. G has a non-removable discontinuity at x equals negative 1. Well, non-removable discontinuity is either a vertical asymptote or a jump. Those are the only kind. So vertical asymptote or a jump at negative 1. At negative 1, there is a jump. So yes, that is also true. Okay, so true, true. All right, G has a non-removable discontinuity, vertical asymptote or jump at x is equal to 2. I go to x is equal to 2, and there's a hole. A hole is not non-removable, a hole is removable, so this one is false. So 1 and 2 only, C. All right, one more type of example. Which of the following functions has a jump discontinuity at x is equal to 3? So a jump is when the limit as x approaches a from the left of the function is not equal to the limit as x approaches a from the right of the function, and neither are infinity. Oops, neither are infinity. Okay, so jump, the two sides don't match. All right, let's look at this one. Parabola, line, continuous everywhere. The only spot that it might not be continuous is at 3. So think about this. We have a parabola up until 3, and then after 3 we have a line. Do they match up or do they not match up? Actually, this line would be going down, but whatever. Do they match up or do they not match up? All right, let's find out. I'm going to put 3 in for this x. I'll have 9 minus 12 plus 1. And that gives me, let's see, negative 3 plus 1 is negative 2. Okay, with another color here. I'm going to do this one. If I put 3 in for x, I'll have 1 minus 3 is negative 2. Those two pieces match. So no, it does not have a jump discontinuity. So not F. All right. This is very similar. Parabola and line. The only place it might not have a continuity, or that it might have a jump discontinuity, is at 3. So I'm going to put 3 in for x. I'm going to have 9 plus 6, that's 15. Here I have 3 times x, I'm sorry, 3 times 4, so that's 12. 15 is not equal to 12. Therefore, we do have a jump discontinuity. So I'm going to keep G. Let's look at H. Now I see a parabola, and I see another parabola. Okay. However, look at how they defined it. This parabola is true everywhere except exactly when x is 3. This parabola is true everywhere except exactly when x is 3. Is it possible for this function to have a jump discontinuity? No. Because of the way they defined it, it is not possible to be a jump. Okay? Because at most, it would have a hole. At most. Or this might fill the hole, but we don't even have to check because all we were asked to do is there a jump? So the right answer here is B. All right. Is that it for me? Do I have a page? Nope, that was it. Alrighty. You guys, I would probably in class ask you to pull out your worksheet because I added a page to the back of this worksheet. I added 2 pages to the back of the worksheet. I would love for you to, you know what, I'm going to see how you do it. Well, since I'm out, let me do one of these with you. Let's turn to your worksheet packet. And let's take a look at number 10. Let's take a look at number 10. Okay. In number 10, we're given this. We're given this. The graph of f, the graph of g. The graphs of f and g are shown above on the interval from 0 to 5. Let h be g of f of x. Find the limit as x approaches 3 of h of x. Or explain why the limit does not exist. Use correct limit notation in your answer. So, if I am finding the limit as x approaches 3 of h of x, I am first going to go inside of h and let x go to 3 of f. Okay? I'm going to write that out. The limit as x approaches 3 of f of x is equal to 2. But it's coming at 2 from above, right? From above. From above 2. So, when I now go to my outer function g, I'm going to find the limit as x approaches 2 from above 2. So from the higher side of 2, of g of x. So the limit as x approaches 2, but from the right, is going to give me 4. So the limit as x approaches 3 of h of x is 4. Okay? Part B. Let k be this function. Consider x equals 2 and x equals 4. Determine whether k is continuous at each of these values. Justify your answer using correct limit notation. Alright, so for x equals 2, to be continuous at x equals 2, the limit as x approaches 2 from the left of k of x must equal the limit as x approaches 2 from the right of k of x, and that must equal k at 2. So, the limit as x approaches 2 from the left of k of x is equal to All right, the limit as x approaches 2 from the left of 4 minus f of x times g of x. So 2 from the left, 2 from the left. I'm going to have 4 minus, okay, what is the limit of f as x approaches 2 from the left? As x approaches 2 from the left, that's going to be a 4. 2 from the left of g, 2 from the left of g, that would be negative 1. It doesn't matter because each of these is 0. The limit as x approaches 2 from the right of k of x is the limit as x approaches 2 from the right of 4 minus f of x times g of x, which will be 4 minus, okay, what is the limit as x approaches 2 from the right of f of x? Well, from the right on f of x, we're back at 4. So once again, this is going to be a 0, but let me go ahead and finish. As x approaches 2 from the right of g of x, that will be 4. But this is still 0. That is still 0. So now we have to say, now we need to find exactly what is k at 2. What is k at 2? Well, k at 2 will be 4 minus, okay, what is f at 2? What is f at 2? F at 2 is 4. What is g at 2? G at 2. G at 2 is 4. So this is 0. And now I can say that k is continuous at x equals 2 since the limit as x approaches 2 from the left of k is equal to the limit as x approaches 2 from the right of k, and that is equal to k at 2. Now we're going to do the same thing for x is equal to 4. So the limit as x approaches 4 from the left of k. All right, this is going to be 4 minus, all right, as 4, I'm sorry, yeah, this 4 came from that 4. Now, what is the limit as x approaches 4 from the left of f of x? 4 from the left. 4 from the left is 3. And now we go to g of x. What's 4 from the left of g? 4 from the left of g is 1. So this is going to be 1 times 1, or 1. The limit as x approaches 4 from the right of k of x. 4 from the right. So I have my 4. Now what is 4 from the right of f of x? 4 from the right of f of x. That's 3. 4 from the right of g of x. 4 from the right of g of x is 4. And that is equal to 4. I don't even need to find k at 4 because I found that the two limits do not match. So I'm going to say k is not continuous at x equals 4 since the limit as x approaches 4 from the left of k of x is not equal to the limit as x approaches 4 from the right of k of x. That's it. Okay, part C. Values of f of x at selected values of x are given in the table below. Okay, what type of discontinuity does f have at x equals 1? What type of discontinuity does f have at x equals 1? Well, at x equals 1, I can look right here and I know that we've got a hole, right? So I'm going to write at x equals 1, f has a point discontinuity, also called a removable discontinuity. Okay. Based on the values in the table, what is a reasonable estimate for the limit as x approaches 1 of f of x? Well, I look in the graph here. It's impossible to know what it is from the graph. It's somewhere on the above 2.5, right? But below 3. But from the table, I see that I'm getting closer. Well, at 0.999, I'm at 2.784. At 1.001, I'm at 2.787. So what would be a reasonable estimate for the limit as x approaches 1 of f of x? What would be a reasonable estimate? I would say a value in between those. True? Maybe 2.7855? I think that would be a reasonable estimate. Write a difference quotient that best approximates the instant rate of change of g at x is equal to 2.5. Write a difference quotient. It's been a while since we've written a difference quotient. A difference quotient is just a quotient where the top and the bottom have a difference in them. That's all a difference quotient is. Okay? A quotient with a minus sign on top and bottom. Okay? If we want to estimate the instant rate of change of g at 2.5, the instant rate of change of g at 2.5, I'm thinking change in g over change in x at two surrounding x values to 2.5. Let's come up. Here's 2.5 on g. Essentially what they're asking for is, what is the slope between those 2 points? So I'm going to use 2 and 3. So I'm going to say g at 3 minus g at 2 over 3 minus 2. G of 3 from the table is, not from the table, from the graph is 1. G of 2 from the graph is 4. So this is negative 3. It is the slope between these 2 points. Okay? Alright. That's it. And number 9 on this worksheet is very similar to that. Alright. That's it. Okay. Tomorrow I'm going to have the test outline for you, and I'll do a few problems from the review.